Okay, so by definition, standard enthalpy change. So when we see this little 0 right there, okay, so we should recognize that as standard, okay? So Atkins, all right, the symbol in Atkins looks like this with a little like cross line through it right there, okay? So that's just their symbology for standard, all right? So the change in enthalpy for process in which the initial and final substances are in the standard state. Okay, well, what's the standard state? The standard state of a substance at a, look, specified temperature. Doesn't have to be, 273 or 298 or whatever. It's just the substance at a specified temperature in its pure form at 1 bar. That's the important thing to note. 1 bar technically represents the standard reference state for standard enthalpy changes. Okay, so we have to note at which temperature we're looking at the data, but by using that standard, we recognize it's 1 bar. Okay, so here's our techniques. So these aren't the only techniques for doing standard enthalpy changes. Just a couple that I want to highlight. So adiabatic bomb calorimetry, or sometimes this is called constant volume bomb calorimetry. So the adiabatic obviously refers to the fact that it's an isolated system, okay? And it's a bomb. And I actually have one of these things in my lab, and I hope that you're able to use it next spring. I really do. It's a very cool technique. I'm going to talk about this. I have a whole slide for this next. But this technique is great for characterizing chemical changes, most notably combustion. Okay. And then for physical changes, differential scanning calorimetry, often just referred to as DSC. So DSC can also do chemical changes, but most notably, it's used for characterizing physical enthalpy changes. So let's talk about that one, okay? So the physical standard enthalpy change, so I realize this is all kind of small, so you can see here, that's table 2.4 in the book. So this is just giving us all kinds of physical changes that we could talk about, including a handful of chemical changes, right? So like ionization or electron gain or reaction or combustion, right? So it's not just physical changes, but these are enthalpies of any type of change. But I just want to highlight particularly the physical changes, okay? Such as the enthalpy of fusion, which is the change in heat accompanied when a solid becomes a liquid, or the enthalpy of vaporization, so the change in heat accompanied when a liquid turns into a gas. And I also want to note that we're going to have a whole entire chapter, a whole entire module on phase transitions. So this is just introductory material for now, okay? So this is just a very, cartoony picture of a differential scanning calorimeter. They are quite complicated devices. There's a lot of students in senior seminar who have presented stuff on DSC. So I would encourage you to look one up. Look at what they look like. The electronics are wholly ungodly complicated, okay? But simply, the DSC contains a sample compartment and a reference compartment, right? So the sample compartment, this is what you are trying to analyze. That's your analyte. And your reference is some material that is not going to undergo a phase transition at the same temperature that the analyte does, okay? So what you do, you have thermocouples, which is a digital thermometer, right? And we'll talk about thermocouples as we go. Probably more as we get to the end of the semester, and we spend a lot of time making and doing thermocouples in PChem lab. Hopefully we'll be able to do something like that. So you have thermocouples in both chambers, and heat is applied to both chambers. And if you've designed this experiment correctly, then equal amounts of heat are applied to both chambers. You monitor the temperature, and you also monitor how much power or current you are applying to these heaters. And of course, that needs to get converted into energy, right? You actually use electricity to make these things get hot, but you have to, this is part of the complication of the device, is you have to know how to convert that, applied power into actual heat, into how much joules you're giving to the material. And that's where the reference material comes into handy, right? Because if you know, for example, let's say you've applied 100 watts of power to the reference material and it goes up by a certain temperature, okay? If you apply that same 100 watts to the sample, but it does not go up by the same temperature, then you know that that heat is getting pumped into the molecule to undergo some type of phase transition or some type of chemical transition, okay? And just an example from the book, so a lot of you are biochemists, so you might find this interesting. So this is called a thermogram, which is the temperature rise as measured by the thermocouples, right? And the excess power absorbed by the sample, okay? Which eventually that excess power can get converted into excess heat and eventually gets converted into excess heat capacity. So notice this scale is millijoule per Kelvin, okay? And so this protein ubiquitin at pH 2.45 is known to undergo an endothermic conformational change at around 45 degrees Celsius, okay? And on this scale, I know it takes off a little bit earlier than 45, but in and around 45 degrees, it's gonna start undergoing that phase transition. So compared to the reference, this ubiquitin sample will require an excess amount of power to get the same temperature rise as the reference material, okay? And so it undergoes this conformational change over these ranges of temperatures, and eventually it will return back, or it won't return, it'll be in some, new phase out here, okay? And you could keep heating up that new phase. You don't just have to do this on one phase transition. So in the case of a simple solid, you could use DSC to follow its transitions all the way from solid to liquid to gas, okay? So that's very brief on DSC. If this sounds interesting to you, I would certainly recommend looking up more stuff. So there's a lot of new chemistry associated with materials. And a lot of people in seminar last year were super interested in materials, whether it be for alternative energy or for alternative building materials. And so the DSC is getting a lot of popularity to characterize newly synthesized materials and their physical properties. So this is a pretty cool technique. Okay, so now bomb calorimetry. So we have one of these in the PChem lab. And it's pretty fun to use, although admittedly very anticlimactic, because you're expecting it to be like a bomb, right, and make this explosion, but it doesn't. Well, I should say it does make an explosion, but it's contained in a giant stainless steel chamber, which we call the bomb, okay? And so typically you pressure, so oxygen input, the unit we have in the lab, we pressurize it with 30 atmospheres of oxygen, 30 times atmospheric pressure. And that's to ensure complete combustion. You load your little sample in here, okay, that you want to analyze. And in the bomb we have at HSU, you can do solids or liquids. You can't do a gas in there. And that's because you'll end up having a pretty large explosion, something that's too great of a pressure change for the bomb to handle. But liquids can be done, and a lot of students in PChem lab have found it really interesting to analyze gasoline or oil or various hydrocarbon for its energy content. Okay, so then now surrounding the bomb is a water bath. And you notice the thermometer is not in the bomb itself because it would blow up. So the thermometer is in the water bath. And so what happens once you fire the bomb and it explodes the material, the heat from this is allowed to go into the thermometer, okay? So really the insulation of this is around the whole device, right? So that it's adiabatic from the outside. So this water is in direct contact with that stainless steel chamber, and you don't want that part to be adiabatic. You want it to be able to change the temperature of the water. And so just like in calorimetry, right, I can write QV equals CV delta T. So there's a change in temperature accompanied with the combustion of the material, and that gives you a correspondingly some amount of heat evolved in the reaction, which then can be related to these values right here. So these are so delta CH, that's the heat of combustion. So in other words, so for benzene, you see right there C6H6 plus O2, and we know it makes CO2 and H2O. It really does go to complete combustion because there's 30 atmospheres of oxygen pumped into this thing. So I have to balance this equation. I can't just leave this hanging. It drives me crazy. So 6 CO2s, right, and 3 waters, and that gives me 12, 15, so that's 7.5 oxygens. Okay, so let's rewrite that. So C6H6 plus 7/2 O2, okay? So all the oxygen gets consumed. All of the benzene, if we were doing benzene, gets consumed. This quantity of heat gets released, which corresponds to a certain change in temperature of the water bath. And then now this CV, really for bomb calorimetry, this represents the heat capacity of the entire apparatus, right? Because there's some water in there, and the device at HSU, it's 2 liters of water. It's a lot of water, 2 liters. And we typically put less than 1 gram of material. So that's kind of impressive when you think about it, that combusting, about 1 gram of material can get a measurable temperature rise out of 2 liters. It's typically like 2 or 3 degrees temperature change. And the thermometers, the thermocouples that are used are highly precise. So they have to be, you have to have a lot of significant digits to get reasonable data out of the bomb calorimeter, okay? So the bomb calorimeter starts by putting in a known material, a material with a known heat of combustion. And that allows you to calibrate the instrument, right, to get the heat capacity of the entire apparatus. Then once you know the value of the heat capacity of the entire apparatus, okay, and typically, using this form, right, Q is M times C times delta T, then you can, using the mass, heat capacity of the entire apparatus and so forth, right, we know that these equations are just connected by the molar mass of whatever you're dealing with. Then for an unknown material, that allows you to get determine its enthalpy of combustion, or in the case of like a fuel, we could call that its energy content. Or even in the case of food, there are some biologists who actually put sugars and proteins and actual animal food in there to see what its energy content, the caloric content of that fuel or food. Okay, so it's pretty cool. Okay, so just one last quick section on thermochemistry, standard enthalpies of formation. So the standard reaction enthalpy for the formation of its compounds from its elements and their reference states. And again, the reference state of an element is its most stable state at the specified temperature at 1 bar. So if I had H2O at 298 K, then obviously its most stable state is a liquid, okay? So what do we mean by then this standard reaction enthalpy for the formation of compounds from its elements? What does that mean? So look, on this chart, this is the same chart I showed you. We have enthalpies of combustion, Now here are the enthalpies of formation, okay? So for example, the enthalpy of formation of benzene would be given by the following. I would need 6 carbons. And so you notice that this here is at 298K. So the most stable form of carbon at 298K and 1 bar is going to be solid, okay? Plus, I'm going to need 3 H2 gases, because the most stable state of hydrogen at 298K and 1 bar is in a gas. And when I react those together, that's going to make C6H6 liquid. So this is what we mean by the standard enthalpy of formation. And just to remind you, right, when I look at the standard enthalpy of reaction, I'm going to write Rxn for reaction, okay? We recognize that it's the sum of the products of their respective enthalpy of formations, okay? Products minus reactants, and then that's delta HF0, okay? So when we go to calculate the enthalpy of reaction, so for example, if I was doing this equation right here, if I was calculating enthalpy of, let's say, combustion, okay, I would need the standard enthalpy of formation of each one of these states. And hopefully what you remember, states that are molecules that are already in their standard reference state have an enthalpy of formation of 0, okay? So, so for example, like hydrogen gas would be 0, okay? Carbon, solid, would be 0 for its standard enthalpy of formation, all right? So that's just all good review from your Gen Chem days. And we're not going to really do a whole lot with thermochemistry in this class. We're more, as you can tell, kind of getting into the, you know, the derivation and the laws and the discovery of thermodynamics, okay? But occasionally we might talk about stuff like this, and if we do anything in the lab, which let's just leave that hanging for now, we'll talk about this stuff a lot because a lot of students have had a lot of success and fun using the bomb calorimeter to do some of their projects. So that's all I really wanted to say about thermochemistry and standard enthalpies of formation. So I'm going to have one more lecture after this for this chapter, and it will be a fairly math-intensive one, okay? Just to be aware, we've got one more lecture to go that is going to be fairly calculus-intensive, okay? I'll see you later, folks.